Welcome back to our lecture series on automated machine learning. AutoML, the age of foundation models is still our topic. And now we'd like to talk about how we can augment Bayesian optimization with large language models. So, Bayesian optimization effectively optimizes expensive black box function, for example, used for HBO, or we also have seen it for neural architecture search, but struggles with sparse initial data and the surrogate accuracy, especially in early stages, where the model simply, or the surrogate model is underdefined. Large language model demonstrated already exceptional few-shot learning and contextual understanding capabilities. And the idea is if we can bring both words together, we get the best bounce out of both. We're getting the valuable domain knowledge for the LLM and the efficient optimization from BO. We discussed two exemplary paradigms now. The fully LLM-driven components idea from Lambo and the more hybrid trust-based frameworks that integrate statistical models, which is called Linbo. First of all, Lambo, proposed in 2024, it's more directly using LLM as the core component for nearly everything. So it translates the BO pipeline into natural language and then enables the LLM to process the optimization history and suggest even solutions. First of all, how do we sample candidates? So candidate configurations, for example. We're saying we would like to target a desired objective value, which is called C prime. And we would like to really have that concretely as possible. And C prime is more defined by the C min and C max, so the maximum minimum we have seen so far, and saying there is some kind of alpha value also being in addition, and saying how much better we would like to get, for example. So alpha acts as an exploration parameter for Lambo, dictating how aggressive to exploit beyond observed values. So positive alpha leads to better than C min, and negative leads to conservative within observed bounds. And what we're doing is we can sample our alpha in each iteration and then saying, okay, what kind of desired objective I now would like to ask my large language model to generate. Very important, we more condition our large language model really on these kind of good regions, and saying I would really like to have my performance values, which should be here, sorry, C prime, not S prime, directly. And we don't say that, should be everywhere C here. We don't say that we only would like to be better than that, right? But we really say, okay, we would like to have a region where we have the performance of C prime. Then we're doing as next question how to do that actually with a large language model. So of course we anchor the LLM by defining the hyperparameter space, the metric, providing data set meta features and descriptions like dimensionality, class distribution, and so on, to zero-shot warm start our LLM that it knows more or less what we are talking about. Then natural language translation should be more or less obvious, right? We translating everything to strings and saying something like max versus 50, min, simple, and so on and so on. And accuracy we observed is 0.9. But everything is in context learning, so we're directly feeding in and getting more or less samples or performance out. We're also using the LLM as getting performance values, so really as not only for sampling, but also as a surrogate model, in addition for the sampled configuration. And what we're doing, we query the LLM not only once to get one performance, but n times. And what we're doing to get more now distribution over possible performance values is we permutate our metadata, which is what is stored in our previous history data. We're simply permutating that. It makes sense from the perspective and saying, okay, there's anyway no ordering in our history data. Therefore, we can shuffle that, we can permutate that. That gives you good estimates on the entire possible distribution of performance that you can observe, and therefore then estimate mean and variance or standard deviation from that. I don't know. Nevertheless, it's a way to do it. putting everything more together here, it's how it's done. That's the picture from the paper. You need to know is that S is a cost value, a specific configuration. They don't call it C as in our slides, but F. And H is more or less what we call lambda normally. So what we're doing is we warm start Lambo with, as I said, this kind of data set with attributes, the machine learning, what kind of hyperparameter it has, and so on, and then having a prompt what to do. Then we sample possible candidate configurations, giving that kind of information and everything previously we have seen, and then it really gives you for a specific here, for a specific performance value we also sampled as described before, and then we're getting many different configurations from Lambo, from the LLM behind that, and then we're using the surrogate model on top of that, again large language model, in telling us how good most likely these kind of configuration will perform. So we're asking it in addition now, here we conditioned, now we're asking it, but nevertheless, this tells us exactly what it is, and doing it by permutation in here, that we're getting several performance estimates for configurations and having mean variance across that. And then we can use, as always, an acquisition function, which we know from Bayesian optimization, like EI and so on, to decide now what is the most promising configuration we should actually doing the evaluation on, so really spending the most time. And then we're adding that to our history data set and doing that again. That's the entire idea of Lambo. Limbo, in contrast to that, is more trying now to get those words together a bit more and saying pure LLM optimizers such as Lambo lack explicit calibrated uncertainty. So that's what my comment on it already, right? These kind of playing with permutations and hoping that we get a good performance distribution is problematic in a sense. And here they try to use actually still Gaussian processes and BO ideas combined with suggestions from LLM, and then getting the best out of both worlds. How it's done, they're saying that different kind of ways. So traditional BOs more as we have our initial data set, we asking the GP and asking GP and so on. Or we have these purely LLM things, so we're asking the LLM again and an LLM. Or what we now will talk about are these three different kind of ideas. Transient, justify, and constraint, which will I explain in a second. Transient mechanism is more very easy one and say, okay, from time to time we would like to use CGP and from time to time the LLM. So in each iteration there is probability PT or 1 minus PT. We're using the one or the other surrogate model to get a new configuration. The important thing is that PT is monotony increasing with a certain schedule, approaching 1 in later iterations. So the idea is we're starting early on more with the large language model, has a higher probability, and over time the probability goes more and more to the GP because then the GP has seen more data, should be more trustworthy, maybe more efficient in what's doing, and therefore we would like to go with the GP over time more and more. The idea of justify and constraint is a bit different. So justify is the idea we use the GP's acquisition function, whatever that is, for example, UCB, to validate the LLM suggestion. So the LLM is our sampling mechanism. And now we would like to see whether that's more proposing something reasonable. And for that, we're more using here our GP with UCB as an acquisition function and saying the best one we have seen so far, or what GP's optimum could be on both, either on the history or on the entire posterior distribution. And then we have a bit of a slack term, or so we have a bit of a stressor and say, okay, we can be slightly different than that. So that's more a hyperparameter of the method, and then seeing whether the UCB value of the proposed configuration of the large language model actually is in the same ballpark more of what GPP would believe. If not, it's rejected and we could ask the LLM for something better. The other idea is the constraint variant, where we're saying we treat the LLM suggestion as a potential optimal design and refines the GP posterior via this kind of constraint. So we're saying more or less there's a constraint that the cost on that kind of configuration by the LLM has to be better than the best one we can observe from our previous GP. So say, okay, we treat this more or less as an optimum and modifying GP based on that. Nevertheless, we can then fully leverage all the properties of GP. We only have biased it in a certain way. So by utilizing this rejection sampling dynamic, accept the LLM suggestion only if it aligns with the updated posterior support then. Which again was in that mindset, if it's the LLM is doing complete bullshit, we should not use it. If it's fine, we can leverage that information. The main takeaways from these two approaches is that we, of course, using, as we often do with large language models, these kind of context. We have a contextual representation of a search space, of metadata, and so on, that helps us to go with very good configurations early on. We also have the uncertainty calibration, which is essential. We have seen this kind of permutation where I was already commenting on, could be not optimal, but with this kind of rigorous uncertainty quantification combined with GPs, we can even have long-term conversion guarantees still with that. So therefore, hypergeology seems to be quite optimal. So integrating heuristic or context-driven bias with traditional statistical models leverages the early stage strengths of the former and the asymptotic reliability of the later. And this more leads to that trust requires verification in a sense, right? So it's not like we blindly accept what the LLM is doing, but we verify this, for example, with a GP or with other surrogate models, and then only doing it based on these kind of theoretically grounded approaches, mathematically frameworks, to really drive the optimization. With that, this gives you hopefully yet another perspective on how to leverage large language models in the age of foundation models. And I hope to see you also in upcoming videos. Bye.